Dr. Kiss couldn't be here today because he was sick, so I'm taking over for him. So I apologize if this is a little rough. It's kind of last minute. We would like to present some research that we have been doing on non-trivial patterns in networks of electrochemical oscillators. Networks of chemical oscillations have been seen in discrete units as well as continuous media previously. And some examples of those are continuous stirred tank reactors, VC beads, catalyst particles, and even electrodes. Many different types of synchronization type patterns can be observed within these systems, and such processes can often occur in different types of real-world systems as well, such as biological cells or the power grid. Generally, the coupling between these can sometimes be known or unknown, depending on the type of system. And so our question was, can we generate these novel types of patterns that you see in these systems in our electrochemical ones? And so our experimental setup consists of a 3-electrode electrochemical cell with a platinum counter electrode, a mercury-mercury sulfate reference electrode, and a nickel wire working electrode. We can control the behavior of the system through many different types of control mechanisms, even through the circuit potential, electrolyte composition, temperature, electrode diameter, or the external resistance. And we can see a variety of types of nonlinear behavior in the system depending on what types of conditions that we apply, such as smooth oscillations, relaxation, or chaotic oscillations in the system. Today's talk will be mostly focused on the smooth oscillators. And okay, so next we can apply a bunch of electrodes, an electrode array into the system, and apply coupling between those electrodes through the addition of a resistance. Now, these resistances can be applied in any sort of it can be applied in any sort of way to form any sort of network. So what I'm showing on this slide is a chain, but you can very well imagine that this can form any type of network topology just depending on where we apply these coupling resistances. With two oscillators and we couple them through a cross resistance, we can see that if the resistance is sufficiently large, there is no synchrony between the two elements. However, as we decrease that resistance, the coupling increases, and eventually we get to a point where we see synchronization between the elements, such that there is a locked phase difference between the elements, as you can see here. Now, if we increase our system and global coupling in the system as well, so more than two, there is a transition between desynchrony to synchrony in the system that happens at a critical coupling strength. So the question becomes, how can we obtain unique spatiotemporal patterns in this system? And the way that we are attempting to do this is through heterogeneities either in the oscillators themselves or the network. We can apply delays into the system or even nonlinear interactions between the elements in order to produce unique spatiotemporal patterns. One such example of this is the extended triangle network, where the densely coupled center forms a synchronization cluster, while the periphery elements are at their own unique frequencies. And as you can see in the current versus time diagram, the black are the core elements that are firing together, and you can see that the other ones are phase slipping to that core. And so what this shows is that the position of the element, in addition to its natural frequency, is important for determining clustering behaviors, and also the patterns that you can observe on a network can often give rise to spatially organized partial synchrony states, or SOAPs. Now, SOAPs can also occur, we have shown to occur through a chimera mechanism as well. This chimera mechanism requires nearly identical oscillators such that the frequencies of the elements are within 1 millihertz of each other, and there needs to be a large local coupling as well. As you can see in the figure, each element is connected to 7 elements on each side of its position. And then there also needs to be a sufficient delay or non-isosynchronicity in the system through the coupling in order to observe the chimera state. And so When we couple this up, when we leave it uncoupled, you can see that the frequencies of them are very similar. However, when we couple them into the topology, you can see that there is a synchronized portion, and there's also a desynchronized portion of the elements. And you can look at the mean field, which is just a single oscillator's looking at the single oscillator's phase with respect to the elements that are coupled to it. And you can also see there in this plot that there's a group that is synchronized, and then there's a group here in the center which remains incoherent to the synchronized group. However, this chimera state is fragile in the sense that we can only see it temporarily over a course of an experiment, and is intermittent. It fades with the clustering, so we can see it here, and here. However, lately it's been shown that robust chimera states can also be observed. Peter Ashwin showed that explained that there's a weak chimera system where elements can be connected through a chain recurrent flow invariant set, such that there are trajectories where there's a mean frequency between two elements that is non-zero, while another group of elements has a mean frequency of 0. We aimed to observe this experimentally as well, and so what we ended up doing was using a small number of oscillators, 4 oscillators, and connected up globally with some weighted connections. It can also be observed with larger heterogeneities than the other chimera state, in the sense that we don't have to have a strict frequency difference of 1 millihertz. And the weak chimera state can also occur very robustly with higher harmonics in the interaction function. And so this is a diagram of our experimental setup. We have 4 elements that are connected at a coupling strength K, and then there's a scalar epsilon, which weakens the coupling strength between the two groups. So that way there's this there's intergroup and intergroup connections in the system. The interaction function that we employed on the system is described here. We collaborated with Chris Sebek on this as well, where he was able to show in the Oscillator system this weak chimera state, as shown down here with the frequencies and the epsilon value, the scaling of the epsilon value. You can see that there's one pair of the elements that's at a different frequency of the other pair. However, there's a threshold where around 0.64, where the two groups will synchronize together at the similar frequency. And so, in order to apply nonlinear interactions in our system, since resistance is linear, we had to use a engineering method through a feedback system in order to get nonlinear coupling in our system. So this is done through the electrode potential, where the electrode potential of each electrode is collected by a computer, and then we feed back a certain VT unique to each electrode through this equation here, where we have set a V0, or a set potential, a coupling strength, and then this is a adjacency matrix, so that determines which elements are connected to each other. And then this H function is our interaction function, where it has a linear term and a quadratic, or a second order term. And the strengths of those terms can be controlled through a feedback gain, K1 and K2. And there's also a delay that can be applied uniquely to each one, tau1 and tau2, as well as an external delay, which is applied globally to both the linear and nonlinear terms. And so when we set the tau values and the k values so that we can get this nonlinear interaction to match the function provided to us by Chris Sebek. And we found that our R value in our interaction function is about negative 0.4. And with epsilon equal to 0, So where now we only have two groups, we're able to observe as we increase the global delay, external delay of the system, we can observe a bistability between an in-phase and antiphase state such that we can take one group and place it in phase and another group and place it antiphase, and then provide coupling between them. When we apply this coupling, what we observe in the phase difference between the elements over time, we can see that the antiphase group remains antiphase, and the in-phase group remains in phase, and then there's the phase difference between the groups is phase sloping. I don't know if you guys can see this video. Oh. The antiphase group is rotating around the phase space here, and this is in reference to the in-phase group. So the in-phase group, it's in a co-rotating frame to the in-phase group, so that's why it's remained locked over here at an epsilon value of 0.1. So we can see that the antiphase group is slipping to the in-phase group. You can see that many different values of epsilon as well. So here's the frequency of the groups to the epsilon value, and so this is the 0.1 value, which is being shown over here. We also observed it at 0.5, and then we can see a transition to the to both of them going to the antiphase state at around 0.8, and then they become the two groups are synchronized to each other to where now there's no phase slipping between the groups, and so we lose the weak chimera state. And so to conclude, the synchronization behavior in heterogeneous networks can often show partial synchrony states, often through localized substructures in a network. And what we've shown here today is that we can observe two types of chimera states in our system: a Karamoto type chimera with linear interactions, which is found to exist on short time scales, and also a weak chimera with the presence of nonlinear interactions. And that one is much more robust. With that concludes my presentation. Any questions?